So this is the third video on simply supported beams. I'm probably going to go a bit faster in this video because I've gone a bit slower in the previous ones, and you can, they explain things maybe that aren't explained. Of course, you can always email us questions, and you can always try and pause me and rewind me and hopefully get a bit of understanding there. Okay, so let's look at our thing. A light beam of span 5 meters is simply supported at its endpoints and carries load that varies uniformly with x. So this uniformly means, okay, so the load is going to change and it goes from 18 to 12. We'll draw it as a picture, I think. Find a formula for the load per unit length. By solving this, find the bending moment at any point, also find the maximum value of the bending moment. Okay, let's draw a picture. So this time, I think in the previous example we didn't put a w-axis, here we will. So what have we got? So simply supported anyway. There we go. We said we're going to put in, so that's the x-axis, well, we'll see it in a second. We'll put in the w-axis this time. It's helpful. And here, I definitely think the way that a mathematician would draw this load is makes things a little bit easier than the way an engineer would. I will explain the difference in a second. So this is the x-axis here. Okay, and the load, it goes from 18 kilonewtons per meter here, that's 18, down to 12 here. So for it to vary uniformly means, what it basically means is that if you go over, say, a meter here, it goes down the same as if it varies the same everywhere. So a meter here, it'll vary the same as a meter there. That's kind of basically the idea, which means that you can argue that the slope has to be the same, which means that it's a straight line. And knowing that it's a straight line is vital. As an engineer, you might draw these things, but I'm not going to do that here. Now, strictly speaking, this comes down, but the thing that we do mathematically doesn't go down, but it doesn't matter because points that are off the beam are just not of interest to us. Okay. So all day long, so this is it. It's a uniformly varying load, or a linear load. That means the load varies like this, and it's a straight line. So the big picture you're thinking is y equals mx plus c, and of course the y here is the load per unit length. So of course it's not y, it's w, and in fact it's going to be w of x. Now, what's the slope? Now, there's kind of a crap way and a good way of doing the slope. The crap way is make coordinates out of this, 0, 18. Make coordinates out of this, what's the span here? 5, 5, 12. And do your slope formula to y2 minus y1. Not a big fan of that because if you've got a picture in front of you and you understand what slope is, you can more or less just write it down. So slope is rise over run. Now, there's one thing you have to be careful of here. The slope here is negative. So I'll explain the 3 ways you can get it. So the first, okay, it's negative slope. So the rise, it's going from 18 to 12. So the rise is 6. And the run, it's going from 0 to 5 is 5. That's the slope. Now, that's kind of saying, oh, the rise over the run, and it's negative. Alternatively, you can say the rise is minus 6 over the run is 5. So you get minus 6 over 5. Which is the same as minus 6/5, or you can go from here to here and say the rise is 6, but then the run is minus 5, and you get 6 over minus 5, which is the same as minus 6/5 times x, and c is where it cuts the y-axis. Well, here's the w-axis, 80. So that's what's going on here. Okay, so so that's the first part. This is basically our answer. Sure, we'll throw it in the box there. I'd prefer w of x, but there you go. And then it wants us to solve the second derivative of the bending moment is equal to minus the load per unit length. So I must multiply this by minus 1, and if I multiply everything here by minus 1, I get minus, which is plus, and minus 18. So we have second derivative bending moment, which is m double dashed of x is equal to minus load per unit length, which is 6/5 x minus 18. We need to anti-differentiate this twice. I'll do it once over here and once down here just for space. So anti-differentiating both sides. The antiderivative of the second derivative is the first derivative. We're going to fix the constant 6/5. And what's the crack with x? The antiderivative x is x squared over 2. So there's no need for step functions or u's or deltas here if you've got a linear load. Then what is the antiderivative of minus 18? Well, you'd need minus 18x to differentiate to get minus 18. I pick up a constant, and if you start doing your exercises, you get used to it. It is RA. Okay, and now we'll go at it again. Another antiderivative. So the antiderivative of the first derivative is the function m of x. Now what are we going to do here? So this is a little messy, but like if you could multiply this, like how do you multiply fractions together? Top, top, bottom, bottom. So it's 6x squared over 10. I'll just take this away just a little bit. So this is the kind of little stupid algebra things that will be catching you. So 6x squared over 10. And then 6/10 you can divide above and below by 2 is 3/5. 3x squared over 5. You can divide above and below by 2 because you can multiply above and below by a half. Half over half is 1. And 1 by anything gives you the same thing. So this first thing here is actually 3x squared divided by 5. So it's like 3/5 of x squared. I could probably explain that a bit further, but hopefully it's just something that you get right. So this is 3/5 x squared. So if I'm anti-differentiating, I fix the 3/5. Done. And anti-differentiate the x squared. The antiderivative of x squared is x cubed over 3. And then fix the minus 18. What's the antiderivative of x? We remember this like x to the 1. So this gives us x squared over 2. Plus antiderivative RA is RA times x. And then the second constant here is MA. So now we apply the boundary conditions. The first one is that MA is 0 because it's simply supported. That's gone. There's just a reference here. You can set it, or you can find the total load here. It's not too hard. There's two ways. You either turn into a rectangle and triangle, or you turn into a rectangle of height 15. So 75 will be the total weight, and RA plus RB must add up to that, but they're not equal because RA is going to be bigger. So I think we said 15 by 5, what's that, 75? So half of that is like 38.5 or something like that. We'll expect RA to be bigger than 38.5. Okay. So we want to find RA. We need to use the other boundary condition, which is that the bending moment at 5 is equal to 0. Okay. So bending moment at 5 now we need to sub in x equal to 5 into all this. Now we'll do a little 3 divided by 3 here is 1. That's gone. So 1/5 x cubed minus 18 over 2 is 9 by x squared. That's 5 squared. Plus RA, which is what we're looking for here, times 5 plus 0. Well, what does this equal? So it's the bending moment of 5, which is equal to this, and we know that the bending moment at the ends at 0 and 5 is equal to 0 for simply support. So this is 0. So we should be able to find RA. Okay, so this is just an equation in RA, which hopefully isn't too bad to solve. So this is 5 cubed divided by 5. That should be 5 squared. Actually, I'm just going to bang this into the calculator instead. So you get minus 200 here. In terms of signs and stuff, you also expect RA to be, certainly in this module, to always be positive. It's possible maybe to be negative, but not in this module. So I got a minus 200. I don't want that. I'm trying to get RA on its own. So I add 200 to both sides. It's worth commenting, if you want to get rid of the 5 first, you can. You divide both sides by 5, but when you got a sum, you divide both of them by 5. So you end up with minus 40 plus RA equal to 0 divided by 5, which is 0. You end up with the same thing, but it's better to work from the outside like an onion. So we're going to add 200 to both sides here. And now we've got to multiply by 5. We need to get rid of that. We need to divide by 5. Divide both sides by 5. This will get rid of the 5. I'll have RA, and 200 divided by 5 is 40 in kilonewtons if we want. So we present our answer then. As we said, the 3 divided by 3 is 1. So this is 1/5 x cubed. Minus 18 over 2 is 9 x squared. RA is 40 times x. So this is the bending moment at any point along this beam. And we might just remark, this is bigger than half. I'm going to write, it's not great notation, because usually the W stands for load per unit length rather than load. I'll use maybe this big W. It's bigger than half the total load. If you calculate the total load, it's 30, what did we say, 75? Half of that, I think I said 37.5. It's bigger than half of that, because more of the load is on this one. This one then will be, well, this one will have to be whatever, 35. Okay. Is there any more question here? Find the maximum value of the bending moment. Now we'll just draw a picture of it. Now here you'll note that I've drawn it like you do, with the bending moment below, even though it's positive. So we want to find, the maximum value. So there's 2 ways you can understand this. One is you use your engineering knowledge, which says that the bending moment, the maximum bending moment at the shear equal to 0. And then all you need to know is that the shear is equal to the derivative of the bending moment. So to say that the shear is 0 is to say that the derivative of the bending moment is 0. And you should have the derivative of the bending moment here. Now we'll probably go back and differentiate this. Alternative, that would be kind of an engineering way. Mathematically, you kind of think of this picture and you say, okay, at the maximum, the slope must be 0. So you get there a little bit faster. Realistically, in my opinion, the maths explains the engineering, in my opinion. Okay, so we need to find where the derivative of this is equal to 0. So we need to differentiate this and set it equal to 0. So in terms of space, I think we're going to make it quite small. In fact, I'm going to go back to this. So this, the 6 over 2 is 3/5 x squared. So either I differentiate fx or just go back there. So m dashed of x, which is equal to the shear, by the way, is 3/5 x squared minus 18x plus RA, if I read it from here, but we found RA was 40. Okay, and we want to solve this equal to 0. Okay, so the crack here is you can try and factorize it, and factorizing quadratics is going to be very important in the second semester, but in this first semester it's not important. And anyway, if you try and factorize this, you won't be able to. So you've got an x squared, an x, and a constant. Should be screaming here, minus b formula. So I'm going to do x, let's just call it x, equal to minus b, so that's minus 18, which is plus 18. The minus b formula is something that you're not going to want to make a mistake with, and if you have it in the assignment, you can kind of check your answer. You'll even be able to check your answer with something like this against Wolfram Alpha. Like, you could ask Wolfram Alpha to solve this for you, that's no problem. Maybe just to check your answer. So minus b plus or minus square root b squared, which is minus 18 squared, minus 4 times a, which is 3/5, times c, which is 40. So like, you have to be careful, this is above the line, etc., over 2a. Now here the plus is too big because it's 18 plus, now the square root of anything is positive. So it's, well, if it's a real number anyway. So 18 plus a square root, even if you divide it by this is 16/5 or 6/5. What's 18 divided by 6/5? 15. So this, the plus one is too big. Basically what I'm saying is you get an x value that's like, the beam is span 5. 15 just doesn't matter. Like, this formula mathematically makes sense for all values of x, but we're only interested between x between 0 and 5. So R1 has to be the negative one. So if we bang all this into the calculator, so maybe if we call this x plus or minus, we find that x minus, now what you'll probably do is find both of them and just notice that one of them is not on the beam. So I get an exact answer here of 15 minus 5 root 57 over 3. That's the exact value. You can approximate that using, say, 4 significant figures, 2.417. And what you can do is then, so this is the location of the maximum bending moment. So what you have to do is substitute that into the bending moment function to find the maximum bending moment. And if you throw in, here I'm just going to throw in 2.42, I get an answer approximately 42.9269. Now there's a remark here that's important for later on, particularly in chapter 2, which we'll see. So normally I wouldn't throw in this decimal approximation or even 2.42 because these things are not equal. They're only approximately equal. And when you take a rounded number and put it into a different formula, like we did here, your rounding errors can get a lot worse. And you know, a mathematician would consider this a big problem. Like, so I wouldn't like see 1/3 equal to 0.33. That's just not true. It's only an approximation. But it turns out that there are times when rounding is kind of safe. So at the maximum is an example of this. So if you look at the maximum, if you change the value of x from, say, the exact value to 2.42, or even if you move it like 2.4, 2.5, notice that the bending moment really doesn't change that much. At the maximum, it's quite flat. Similar story, like if you go up something like Mangerton Mountain in Killarney and you go up the top of a mountain is flat. So if you move around, it doesn't change that much. And that's another manifestation of the derivative being 0. So what am I saying here? This is saying that the rate of change of the bending moment with respect to x is 0. It means, now if you move away, it's not 0, but it's still small. So it's saying that as x changes, in other words, as you move slightly away from the exact location of the maximum, the bending moment doesn't change that much. Okay, and that's kind of written down something like this. If you take now this x max in the notation above, x max is equal to x minus, which is this number here at the square root. So in fact, in this example, using the one with the square roots and using 2.42, they agreed to 4 places of decimals. It's incredibly accurate. It's 6 significant figures. But if you do it around x equal to 1, rounding is far more dangerous. So around x equal to 1, you can see that if you move slightly away from 1, you get kind of fairly significant changes in the bending moment. So like if you look at the bending moment at x equal to 1, you get this 31.2 kilonewtons. And if you move away 1 inch, 0.025 meters, you're getting 31.789. Now that doesn't look that much, but it's 500 Newton meters, which isn't nothing. So it's not really safe to round around there. Now we'll talk about the rounding a little bit later. In what we'll see actually later on is the error that's approximated here. We'll learn about this. At the maximum, it's approximately 0. You know, it's 0.00001, but at 1, it's about 600 kilonewton meters. Sorry, 600 Newton meters, as we say. Okay, So I think I won't start the next one, so we'll just finish that there.